Classical versus quantum in pictures. So this is the inventor of this diagrammatic calculus that we've been enjoying so much.
So a lot of things have been talked about this week by different people, so I thought it might make sense to give a little bit of a wrap-up of this program of axiomatizing quantum mechanics. So last time I looked at my slides before I ended, I think I had three big chunks. One chunk was sort of a wrap-up of everything we've seen, including Rose's talk of this morning and things Dushka talked about, and of course the things Samson talked about. The remainder of the talk, I will have a particular focus on models. Like you hear always, model of this sort of axiomatics is Hilbert spaces. Yeah, but there is also relations too. And sometimes Rick even says that there are cobordisms as models, but that's basically the end of the story. So I'm going to talk a bit about which I think are very much still in progress, but very weird, exciting models, discrete models of this sort of structure, which got an amazing amount of quantum features in it. So just the general, I'm going to try to be comprehensive here. So I think this is done. Okay. So the basic general framework, we've heard about this so much, which is just a general way of writing down theories in a graphical language. And just to make some propaganda, I'm currently producing a series of volumes which is called New Structures for Physics, and a lot of people here in the audience are actually contributing chapters to that. The idea is basically to write chapters on the sort of tools we use, but tailored towards physicists who never heard about category theory, who never heard about domain theory. I'm just trying to convey the story how useful these things can be. So this will be one chapter in this, for example. Okay, so this is sort of the general setup of theories, I would say. So what is a theory? A theory is something in which you've got systems and processes of a certain nature. Yeah? So you depict your systems by A and B and these little lines, and a process from system A to system B by some symbol F, which you depict as a box. This is doing nothing process, or nothing happens, depending whether you take an operational perspective or a more sort of observational aspect. This is like first process F, then process G. This is process F on system B to a process G on system C. You can have all kinds of combinations. And for those who know the axioms of monoidal categories, symmetric monoidal categories, they know that these sort of intuitive sliding rules actually capture the essential axioms of symmetric monoidal categories. So basically what you see here is a symmetric monoidal category, avoiding all the horror you get when you go to non-strict situations, which we definitely won't talk about today. So one additional bit of structure which you got in monoidal category is your unit for a tensor, which we think of as no system. So this then is a state. It means you don't really specify where your things comes from, but you can do something with it. Like here is a state, so you don't specify where it comes from, but you've got it available. This is the dual to it. So some people would call this an effect if you've got a physics background. You can think of this as destroying a system, something which typically happens in a quantum measurement. And then if you compose a preparation with a destruction, you get something without an input and an output, but which, as Samson mentioned in his talks, is not a void concept, which can be something like a number. Very important in quantum mechanics because it can represent probabilities. So actually in this language you can compute probabilities. And for example, you can have like closed loops and things like that, and people use this. If you look in the literature of representation theory, a lot of these techniques have been used for a very long time for actual computations. So now, then, is this new? No, this is not new. This is 70 years old, because this thing is 70 years old. Well, 65 still. And you close it down, you get this one. You get this one, you close it down, you get this one. You take this one, you close it down, and you get this one. So there's nothing new there. This is just Dirac notation expanded in 2 dimensions. Okay, so in Dirac notation, we need to turn a cat into a brat. So we will enrich our language with the ability to take something and put it upside down, which of course encodes the adjoint. Which are the models for this? Well, of course, finite dimensional Hilbert spaces are a model. You take Hilbert spaces as objects, linear map as your processes, tensor product to combine system, and the adjoint is then putting things upside down, and the scalars are basically the complex numbers, because all the linear maps from complex numbers to complex numbers are isomorphic to the complex numbers. Category of relations, everybody knows this very well now. The scalars are either 0 or 1, because there's two relations from a singleton to a singleton, the empty relation and the identity relation. Of course, category set already falls out of the boat because it doesn't have a tag. Huh? Yeah. So, okay, now how do we continue? So this is general theories. This can apply to anything, basically. Any world where you've got processes, states, and systems, the previous story applies. So now we want to say something about quantum theory. So basically what we are going to do is adjoining new structure. Like structure meaning really in a constructive way, a piece of structure, a new structural element. And for example, we know that there are entangled states in nature, so we're going to add an entangled state to our system. So that's the piece of structure. We know that we can copy and delete classical states, so we're going to add a copying and a deleting operation to specify whenever we're dealing with classicality. We know that there are complementary observables in nature, so we're going to add two such complementary observables. And that's how we build a theory. It's like build with Lego blocks. You just add new little pieces to play with, and you see how much you can do with these pieces. That's sort of general methodology. So firstly, we've seen this a lot. So quantum structure involves, I'm not going to go give the symbolic definition, adding now this as an element in your picture, subject to the following rule. And this, of course, is if you replace this triangle by a cup, nothing else than this yanking axiom, which you've seen a lot in Samson stocks. And from this on, you can actually start to already do some computations. For example, you define this thing in this yellow box. So this is like any process, and then you put a cup there, a cap there. And then if I also put a cup there and a cap there, I can apply my axiom, and I get this. So the thing which I denote now by F star and represent by 180 degree rotation of the thing in there is a new symbol. So I represent this yellow box now by this new graphical element, which is 90 degree rotation from the original F, 180 degree rotation from the original F, yes? If then I take this piece of wire and I yank it, I get this. If I take this piece of wire and I yank it, I get this. So I just proved this relation, which basically shows that you can take one of these boxes and just slide it along these wires. So this was just a very smart way of representing what actually in Hilbert space turns out to be the transposed. So the transposed you represent by 180 degree rotation, and now you got this nice methodology of just sliding boxes. In principle, I shouldn't have put this star in there, because since it's 180 degrees rotated from that, I know it's something else. So the star is really not necessary to put in here, but I just put it for clarity. So what do you do with this stuff? Well, this is trivial, following this rule, because I can take this one and slide it up there, and it's there. Now, if I pick F such that it's adjoint, is it inverse, meaning F is unitary, then this falls away, we introduce this, and we got quantum teleportation. So in this very general language, there is now already a principle of quantum teleportation. Now, of course, one should be careful here, of course, because everybody knows that this thing, you cannot implement this with 100% probability, because this is something like a projector. And such a projector, of course, is part of a measurement spectrum. So there will be some uncertainty in the ability to implement this thing. And this actually is why you got a correlation between the F here and the F there, and in principle there is some classical flow of information to overcome the non-determinism here. But the idea is simple. Like from this general scheme you get quantum teleportation. Now we can go a little bit more sophisticated. Like maybe Sam knows, I don't know who came up with this idea. As far as I know, it's Salinger. The first time I saw this in a paper was Peter Salinger's paper. So the idea, like I said, is we represent this thing, this F star by 180 degree rotation. The adjoint was just flipping upside and downside. And then it's easy to see that this thing needs to be represented taking the symmetries in space by this flip. And then you can show that all the relations you can prove between f, its adjoint, f lower star, f upper star, are just captured by these 4 rotations, which actually has just 2 symmetries, flip up and flip down. Flip up, down, flip left, right. So it's very simple.
I think some of the things have been observed.
I would assume so, I would assume so.
To be fair, it shows these in early 80s.
Yes, yeah, well,
Was it
I don't know.
tortile?
Yeah.
Yeah?
Sure.
Yeah, you would expect that this has been seen. I just want to be sure because sometimes people claim very quickly that they've seen something somewhere. But anyway, to continue this, so in the Hilbert space case, this is the transpose and this is the conjugate. So, now, the nice thing is that for a simple protocol such as entanglement swapping, you actually already need all of these 4 to make it. So basically again, here, we've got something which is obviously true. I take this one, I slide it there, and then I can yank this bit of rope. I take this one, well, I slide it a little bit. We introduce this, this falls away again, we introduce this, and this is entanglement swapping. Again, a very simple protocol. You've got 2 A and B entangled, C and D entangled. You do a measurement on B and C, and as a result, A and B is not entangled anymore, C and D is not entangled anymore, but now A and D is entangled. So it's one of the protocols which has been. So, but now already, which is nice about this was as compared to teleportation, is that you really need all these 4 little boxes here there. So examples. Bell states as linear maps. So these are Bell states. You just sum the base vectors. This is a Bell state. Now another example, which is the covariism category. So in the covariism category, the objects are just, to make it simple, a bunch of circles. So this is my codomain, this is my domain, and a covariism is some manifold which connects them. Yeah? And in such a category, you also have the same structure, and this is just something like this. This is just your Bell state there. As we saw in Samson start this morning, the moment you've got something Cartesian, things are impossible. You can't have a structure of this kind. You get a no-go theory. So again, I mentioned already there is this issue with that there is an aspect of non-determinism which needs to be corrected there. So we need to find a way to communicate from Alice to Bob, and we would like to see this as part of the picture. Because at the moment this is just implicit in the labels. We want to see a line there, or whatever, which encodes that there is a flow of information from Alice to Bob. For this reason, like in the original paper in which we did teleportation, Samson and I, we relied on byproducts to have this classical flow of information. Unfortunately, this doesn't allow graphical representation, so we needed something.
Well, it allows a graphical representation.
Well, I haven't seen it yet, so far.
Well, it was in my paper with Ross.
Well,
Objective connected, it gets much less feasible.
that's what I mean. I didn't see anything of this. Well, I don't think it's a valid remark. You can't just fill in a line there in any way. So, anyway, so how do you need what can you do? We know that the graphical language, a nice graphical language, applies to monoidal categories. So we need to have a way in the language of monoidal categories to express the fact that something is classical. Now, how do we do it? How do we do this? Well, we've got that quantum data cannot be copied nor deleted, and that classical data can be copied and deleted. A known feature, we're going to treat the first one as a known feature and the second one as a feature. So basically, and this is the nice thing. So, like why byproducts are properties, here we actually introduce an explicit piece of structure, which is this local copying and deleting operation, which you assign to each object. So now we will be introducing a graphical element, something like this which stands for copying, something like this which stands for deleting, and this is what we call classical structure, which we saw in Dushko-Stark and also used in Rosa-Stark. And well, this is definition. It's on some isometric commutative commanoid which satisfies Frobenius equality. And if you want to look at these equations graphically, so here you've got a commanoid equations, no discussion about that. If you've got something and you want to produce 3 copies, then it doesn't really matter whether you first copy the second copy or the first copy in order to obtain 3 copies. It's like same thing, if you copy and then delete, you get an identity. So these things are operationally kosher like it could be, yeah?
But why don't you have this, initial, why do you have to add this? Isn't that just a one qubit measurement, a 2-to-1 qubit measurement?
Which?
Like
No, this is ternary, yeah? This is co-multiplication.
the co-multiplication, isn't that somehow the adjoint of the 2-qubit to 1-qubit measurement, a partial measurement?
Where do we have a measurement so far? I'm building out the thing. The only thing we have is Bell state so far.
So is not this duplication thing? Is that not the adjoint of some partial projection? When you dualize this object in
But you're reasoning in terms of additive structure. There's no additive structure at the moment.
Yes, if you have byproducts.
There's no additive structure. There's no additive structure anywhere.
Byproducts you can define.
This is purely multiplicative so far. That's the main point.
Yeah, but why you had I'm thinking about your methodology. So you're saying I'm going to bring into the picture 2-qubit measurements.
Wait.
Teleportation.
No. I never said anything like that. So far, we only have like projectors.
Right.
We don't have indexing.
Projection.
We don't have indexing.
Projections.
Yeah.
Fine with me. So at the beginning, when you're explaining teleportation or gate teleportation, you're using 2-qubit projections, right?
Yes.
I mean, an abstract version of 2-qubit projections.
Yeah.
So I wonder, why isn't this a partial 2-qubit projection dualized?
Partial 2-qubit projection.
Yeah, something that goes from...
No, never, because for the simple reason, I think, well, anyway, it will become clearer when I give a representation theorem for this why not. But the thing is, if you've got 2-qubit projections, you can make this partial. Now I got 1 and 2, but there's no flow of information. You'll never get the right properties. It's really a new piece of structure we need to put in, which you don't get for free, not by any free construction or anything like that. So anyway, you got this, and then there is a slightly more mysterious, so this is just a sort of unitarity requirement, and this is a slightly more mysterious condition which we took from Carboni and Walter's paper on Cartesian bicategories. Now, the way we came up with it was not by picking it from Carboni and Walter's paper, because I didn't know Carboni and Walter's paper. So the way we came up with this was trying to make teleportation to work, and the classical information flow in teleportation to work, and this turned out to be a key thing to do that. Now, here this actually might explain something to you. So you've got this one, this is this Frobenius law. Now, I plug in these little triangles there, yeah? So this, by the comonoid structure, is identity, so we get this, and now you really see that this idea of having this copying and deleting operation refines the idea of having a Bell state. So how does it refine it? In which way does it refine it? Well, it turns out that it refines it in the sense that as objects you don't look anymore at a Hilbert space, but a Hilbert space plus a base. So this is this theorem which has been mentioned 2 times already, I think, in the talks. The fact that these classical objects, which are just defined in the category of Hilbert spaces, are in bijective correspondence with bases. So it is an axiomatization of the notion of bases, and you can't get the notion of a base out of, say, a compact closed structure for free. It just doesn't work. So I just want to give a little sketch on how the proof goes. So the proof basically goes via Gelfand representation. So we saw this already in Ross' talk, that if you've got a state, then you can leave this to an action on your underlying Hilbert space if you've got one of these classical structures. Yeah, so these are these little cups which we had. Now, by the comonoid structure, this thing becomes commutative, and you actually get a submonoid of all linear maps acting on a Hilbert space. Actually, you inherit, it becomes a sub-star monoid on the underlying Hilbert space. And the reason for that is that if I take the adjoint of this thing, I get this. But by the Frobenius law, which actually implies compact structure, I can do this. Yeah? So here I'm using Frobenius law. And now you see, wait, so I can, somebody's calling me. Hello?
That's Samson calling you.
Okay. So yes, now you see, so you've got, because you've got Frobenius law, you can actually bend this into a new state, and the new state is this thing. It's like the transpose of psi. You can actually prove that having this ability to transpose is exactly the same as having a Frobenius structure. So this gives you a star subalgebra of Frobenius algebra commutativity of the commanoid. Makes you get a commutative sub-C star algebra, and then you can use Gelfand representation to actually reproduce your base of your underlying. And the thing is, this proof is quite tight because there are some very sort of tempting counterexamples which fail to be counterexamples, of course. And like one of the nice counterexamples is the following, which fails to be a counterexample. So,
is that just an example?
Nah, it's better for the story to call it, because it was thought to be a counterexample at some point. So, take this one. So we're back now to look at this. So, if you go to this category of cobordisms, this exactly gives you one of these Frobenius structure I just talked about. It's very easy to see that this gives you one. Now, instead of looking at a Hilbert space, look at a tensor product of two Hilbert spaces. Yeah? And now take the cross-section of this thing. Take the cross-section of this thing in a plane. So then you get this. And now the type is a tensor product because I got two lines. Yeah? And then it's very easy to see that you can get something associative with a unit, satisfy Frobenius, because it's all inherited from the cobordism. But something fails here. And actually what fails is symmetry. The reason, so why? This thing is not symmetric. If I do this, then this is actually equal to, let me check, I think to this, if I'm not wrong. I might have, am I right? No, I'm wrong. Let me see again. Like this part ends up in, yeah, it's this. This is what you get. Now, this of course in the cobordism category, this is still commutative, but it's just like this taking this cross-section, 2 dimension, which makes this thing suddenly becomes non-commutative, so it's not a counterexample anymore.
Do you have over and under crossings there, or is it just?
At the moment I take everything to be symmetric, so it's the same. Doesn't really.
Why not take the cross-section in 3 dimensions?
Huh?
Why not take the cross-section in 3 dimensions instead of projecting that onto 2?
No, I'm just, so the whole line, no, I'm just, so it's not wide. The thing is just saying that if you, the moment you drop symmetry, you have counterexamples. That's the point I'm making. The moment you drop symmetry, you've got counterexamples. And then, like the moment you drop Frobenius condition, you've got very simple counterexamples too. So it's just to say that it's tied in a certain way, this example. So now, so then the next point to make is that all these actions which I gave for this dagger Frobenius structure actually have a purely graphical interpretation, again, which you've seen today already in Rosenstock. The idea is that you just substitute these trapezoids by a dot with 2 outputs and 1 input, and here again a dot. Then if you introduce the following notational convention, that whenever you encounter something of this shape, you represent it by a spider, you can actually prove that any connected network from trapezoids, little triangles, straight wires, cups and caps is equal to a spider. So an important thing here is connected, because otherwise you get just a bunch of spiders, disconnected spiders. And it's easy to show that actually this characterization is equivalent to the definition which I gave before. So now we've got this, and it's then just easy to see that this principle, spider principle, refines yanking. Because this now is equal by the spider principle, and now I can just introduce my triangles again. Whenever I just got a dot on a line, I drop it, and here we've got our initial. So basically we really refine this yanking structure. Examples again, well, I just gave that example there, and in the category of relations you got things like that too. Next step. So now we want to go really quantum meaning. We got incomparable observables, complementary observables, and that's the story we hear this morning by Ross, which basically boils down to you got some structure which you call a scaled bialgebra. So you got the bialgebra law. There is some scalar there. Then you got this law that one color copies the other color. So you've got a green one, and I put into a red one, I get 2 copies of the green one. So, and with these axioms, we are then able to really prove a lot of stuff in gate calculus, like you could see this morning. So, okay. So now the main part, or new part of this talk is examples of things which have all of these features. So I'm not interested anymore in examples which have some of these features. I'm interested in examples which go all the way and have complementary observables, because that's very typical for quantum behavior. So of course, in Hilbert spaces, this is the example Ross described this morning. The copying operation is copying of one basis, deleting of one basis, copying of another basis, deleting of one basis. I just make this explicit here, that basically what we're using is just the idea of having zeros and ones and a minus to build this. So you got some. This is just to introduce my next example. Whenever you got a matrix calculus over a ring, you take matrices over some ring, then the moment you got a 0, a 1, and negatives, you can do exactly the same trick. And you got complementary observables. So this is a ton of examples, but these are typical byproduct categories. These are byproduct categories, and they give you a ton of examples. In coprodisms, would you agree, Rick? It's a guess. Looks very unlikely that you get it. Like rel, problem you don't have negatives. So you can think that on rel there is only one canonical observable which just arises from the 2 elements you got in rel. So it's clearly you don't have complementary observables. So we now have a way to exclude rel from other categories. Huh? But, so my first interesting model is something which I call category of spec. Which is a non-trivial example, which has complementary observables, but which doesn't turn out to have byproducts. So what is spec? Well, there is this guy, Rob Speckens, who has been getting like a flying career with some toy model he came up with in well, the paper is only in 2007, but it's from 2003 or 2004 something. And which the most horrible title for evidence for the epistemic view of quantum states, something like that. So it's like a religious statement about something, and then for that purpose he introduces some toy model. So the principal idea is that it says if we take a set of states, which we call ontic states, which are really about the nature of a system, and then we restrict the knowledge we can have on such a system, then it says that we get quantum type phenomena. Now, he needs to do several compositional and simplificational assumptions to actually get what he is. It's like the construction, his paper is basically 20 pages of construction of his model, a simple model. Now, the basic idea boils down to the following, so that the structure is induced by restricting propositions. So you can't just ask any question on a system. So let's just go back to the situation. You got 4 boxes, there is some ball in the box. You can't ask, like, where is the ball? The only thing you can know about it is, for example, is it in one of these 2 boxes? And you're always allowed only to ask one question. So the maximal knowledge you get is always that you know that it's in either of 2 boxes. You can never know really in which box it is. So that's sort of his physical law induces. So basically the idea structurally is that from states as elements you go to states, now not ontic states but epistemic states, is the states you can know about, to non-trivial subsets, so non-singleton subsets. So that's the whole idea. Now, I think some of you know that I have a got a quantum logic background, and this actually, the best way to feel for me what's happening is like going back to sort of Birkhoff von Neumann style, Piron style quantum logic. So here you got a power set of 4 elements. The power set, so these are the singletons, 2-element subsets, 3-element subsets, the whole set, the empty set. And then in Piron, Birkhoff von Neumann style quantum logic, they say, oh, you can't ask all the questions of your system. Like in Hilbert space, it boils down to the questions you can ask are linear subspaces, not arbitrary subsets. And in this case, this would mean, for example, that you can't ask this question, you can't ask this question, you can only ask this question. So you can't ask all propositions. That's basically, and now when you do this, you get this sort of thing, which is an orthomodular lattice, non-distributive. This thing is non-distributive, it's an orthomodular lattice, and then you can, for example, accommodate 2 complementary observables. You've got an eigenstate of one, these are direct ones are the eigenstate of one observable, these are the eigenstate of another observable. But in fact, it doesn't really matter whether I would do this too. The structure doesn't tell me which are orthogonal and which are not. Basically, the consequence of that is that people, when they say orthomodular lattice, then ortho is a separate structure from the lattice structure. You have your lattice and then you define an orthocomplementation on it, because you've got some freedom in doing that, like I show here. Now, this is what Speckens does. He says, I cut away the singletons, and then he also cuts away this, because if you leave this in, you also get the singletons for some reason. So now, he goes to 6-element. Now I can accommodate 3 directions, like the complex block sphere. So we're actually going from the real block circle to the complex block sphere. But the most interesting thing is the following, that if I remember my points, and I start here, I just go down, I go to the complement, I go up, so I get a uniquely defined complement for all my states. And this is the same for all the states. So you get from the underlying atoms, you actually get an orthocomplement. So the orthocomplement is fixed by this. So it's sort of a much smarter trick to generate. If you're just now interested in generating quantum structures, this is much more powerful, because you get a lot more out of it. And for some weird reason, I don't know why, you get also, maybe this is just like coincidental, you get these 6 instead of 4, which actually corresponds to the 6 90-degree separated directions of the block sphere. So here is the basic idea about this model. So this is the way I'm going to represent it. So you got a box, and then I color 2 of these things red, and it means the actual state of the system is one of these 2. They'll never know which one, so these are the states of my system, so I can represent them as follows. Yeah? So these are the states of my system. So, okay, you've got bipartite systems, so this turns out to be a bipartite state, for example. Now, if one system has 4 states, 4 possible ontic states, and 2 systems has 16, 4 times 4, and then I pick some out. It turns out there are special rules for which you can pick and which you can't, and the rules is basically, if you look at the component system, then again, you can't violate this principle that you know exactly which states you're in. I'll illustrate this later. So this, for example, would be the Bell state, because it's a bit like an identity, you see. Like, of course, a Bell state, you can think of it like an operation. So this sends, for example, this state on this state, it sends this state on this state, it sends this state on this state, and so on. So this is another bipartite state. But this is a special one, because this is one which factors. You can factor this. Like, you really have to think just about matrices now. Think. I take 2 matrices. How do you do that? I get matrix multiplication key.
What is the question?
What?
How do you multiply matrices?
Yeah.
No, by how?
You help me with these things already. Yeah? Yeah, so this is what this picture shows me. That's what it is. And of course you can think of it as a projection too. A projection which takes this input and gives that output. A projection which takes this input and gives the void output. I'm slightly starting to show things which some people in the specular model know they are not in there. He doesn't have projectors, for example. But I think that this is just a mistake, which he actually already has admitted. The reason is when he makes his derivation, then he derives operations in the following way. He looks at the state and he sees which functions are compatible with this principle that you never get all the knowledge about your system. But he never assumes the idea of using relations. And this is relation on the underlying state. He restricts functions for no reason. He just never thought about it that you could take relations as well. And then you get the projections if you do that. So you get a bit more. Okay, here this is a nice one. If I start with this state, then you see I get this one out. So like this one doesn't go anywhere, but this one is doubled. So principle not violated yet. Okay, now here is a tripartite state, so this is one which factors in 3 components. Yeah? Again, you can think of this as an operation of a certain type from 4 to 4 times 4. So this is now an operation which has this ability, it maps 0 to 0, 0. And 1 goes to nowhere, of course. Now, this one is not in his model, and this is a very important one. I'll describe what it does. It's hard to describe it in one picture. So this is what it does. You see what it does? Yeah? It's like the identity which lies on this diagonal. So it has force, and it turns out this is a bad one, because it violates the principle. Now this, what is this? We've been talking about classical objects. If you look to the category of relation with 4 elements, like you take the 4 element set there, this is exactly your canonical classical copying operation. So this canonical classical copying operation on 4 elements in relations doesn't survive this epistemic principle. And this is actually the whole key, as we shall see, to the emergence of quantum mechanical structure. So I'll show you why this violates. So this is the thing. Okay, if I give you this input, then this is my output. You agree? Yeah? So now I take this as a map, and I put this input, then I get this one as output. And that's bad. It's not allowed. So we have to forbid it, so this guy is not in.
This guy has red boxes inside?
Yeah, this is like 4 red boxes inside. I try to vaguely put them in here, if you can see that. There's like 4 of them inside.
And this is being interpreted as an operation?
No, well, you can both interpret. It's all the same when we operate. There's 3 elements.
So it did something that was bad.
As an operation, yes, because it produces a state which is.
You're giving it as an operation from one system to one system.
Yes,
to
that's
the product.
Yes, yes. So that's what it is. So you know the model, so you know that sometimes I sort of sneak out of it and do a bit more, but I'll justify this later. Most people here don't know it, so I'll justify that it's just a mistake not to do it. I'll justify that it's a mistake not. But this one anyway is not in his model. This state, as a state. This would be like this, as a state, you can think of this as a state too. Like just 60 boxes. And this would be the G at Z state for 4-element set in relations. G at Z state is a very important state. This would be the canonical G at Z state in the category of relations of 4 elements. So this one is not in. Which at first sight looks bad, because you want G at Z states. It turns out the G at Z state you will get in will be different. Okay, so now what I'm now going to present is a category which exactly gives you his model. So what do? You take 4, so you take, as qubit, you take 4-element set. So you also consider 1-element set, which is like as a trivial one, the nothing, and then you take powers of this with Cartesian product as stands. Yeah? Then next you take all relations of any relevant type, I mean like from 4 to 4 times 4, not just from 4 to 4, generated by composition, Cartesian product, and converse from all permutations on the 4-element set. Yeah? Then you pick one very special state, 0, which is just a 2-element subset, because that's what states are. And then the third, so this is one ingredient, this is the second ingredient, and the third ingredient is something of this type. You already can predict what this will be. This will be a copying relation, but this is not the canonical one from the category of relations, which is uniquely defined as follows, that it copies both 0 and 1, where 1 is uniquely defined as being the octo complement of 0, and it has a corresponding deleting operation, which is some state which is neither orthogonal to 0 and 1. So you've got a choice of 4 there. This is very much aligned with the story Ross was giving, that you had this choice on your deleting operation. So that's what's happening here. So we are defining a copying and deleting pair, and this is uniquely defined. It's very easy to see how it works. So this needs to be copied. So it needs to go to this. This needs to be copied. It needs to go to this. This needs to be a deleting operation. Now again, if we transpose and stuff like that, it's actually also this must be giving you this. This is the identity, yeah? Because if you take your deleting operation and you plug it in your copying, you need to get a bell state. This is just the transposed. So since we've got this, we also got So that's what I'm using here, just to make it easier to compute. So this is deleting operation, and it gives me the identity. Yeah? So first, so I want this to give this, and I want this to give this. So if I'm brutal, I just give this filling, and this does it for me. Yeah. It turns out that it's a bit too much, that, because I want this one to give me exactly this, and you would see this. If I would have filled in all these boxes, I would get 2 big squares, and I would put 2 big squares. So I have to restrict. And then it turns out that if you want to have something which is associative, that the unique solution is given by. So you've got this box here, you've got this box there, you've got this box there, and then the other one is in there. You see how they make with the 4 of them. It's very hard to depict it like so. You go in here in this box, and then the second slot there is another purple one. So here you've got this, and then if you go through the wall in the second slot, there is that one and that one, and that is the unique solution to this. So this is your new GZ state. It looks very different than you would have expected. But
how are these 3 perfect things on the top related with this square?
so this. So if I plug in this, then I see this one, and this gives me this. I see this one, and this gives me this. This one gives me this one, and then that one internally gives me that one. It's like this one sees this one, so gives this one. This one sees that one, so gives that one. It's like how do you call it? I don't know how you call it. A matrix which is like a cube or something. Like it's not like a 2 but 3-dimensional thing. Like I don't know how you call this.
Well, some people just draw bigger matrices.
3-dimensional matrices.
Well, you put the layers of the matrix as minor, so bigger.
Yeah. Okay. So but anyway, so this is how it goes. Now, what is the proposition? That the pair of this copying operation together with my plus is a classical structure with 0, 1 as its classical points in the sense of Ross explaining this morning. So these are the things which are copied by it. Then that all the other pair, if you take this one and then you start like transforming it with your symmetries, then you get a bunch of classical structures with either 0, 1, plus minus, or minus minus I as its points. And basically you've got 3, in the sense of Ross explaining this morning, you've got 3 complementary observables respectively corresponding with the x, y, and z direction. So this is what comes out. So just to go back, so this is the category which does that for you. This is the category which does that for you. So it's quite simple. It just has 3 generators within the relations. So now, this is a comment for those who know Bell and Rob Spekken's model, and just to say what's wrong with it. Because we've got copying and deleting, we also got a Bell state. That's just what I'm explaining there. Just compose them. And then the moment you've got a Bell state, then you inherit compact closure from your relations. So obviously you need a compact closed structure because you got this Bell state. And then you get this correspondence between bipartite states, operations, and bipartite effects. Now if you got any theory which is closed under composing operations in parallel and sequentially, which is like a very obvious physical requirement. If I've got one process and then I can do another process, then the composite should be part of your theory. Same if you've got some process here, some process there, then doing them in parallel should be part of your theory. Just under this assumption, together with the fact that you've got a Bell state, you know that each such model should satisfy this. And this actually is not true for Specker's model for the simple reason that he forgets like considering relations when he defines his operations. So basically what we've constructed is the compositional closure of the Specker's toy model. That's what we constructed. But a very simple definition. Like the definition is very simple now, just a category from tree with 3 generators. Okay. So corollary, we have G and Z states because those are these things which are constructed, this delta force, but they are not inherited from REL. They are different beasts. And then a corollary of all of this is that all our results we've ever so far obtained in categorical axiomatics apply to this model. So Speckles goes then through in his model to show that you can do teleportation, that you got all kind of principles, but they just follow for abstract categorical reasons, all of them. So all the things like CPM construction, the way you convexly close, all these things just apply. So you get all this for free for abstract categorical reasons. So,
You sure you have the Fourier transform?
huh?
You really have the Fourier transform?
That's what Ross showed this morning.
So,
Just get all that for free.
I don't know what you mean by get all that for free. I mean, Ross showed us how to reason about the quantum Fourier transform using categorical tools. It's not the same as getting it for free.
I mean,
There's something that exists there that does that.
Yes, so
does it give you the right? Does it give you something
Ah.
that sets the right outputs for the right? I mean, you have
So the idea here is, do I have in this simple theory counterparts to things I've got in quantum mechanics? And so I'm not sure. I think the embed. So the question you are asking is, does it perfectly embed into what quantum Fourier transform is? What?
Probably not enough points to get.
Here there are actually enough points. Here there are enough points.
You have enough points. So the point is that you actually have an arrow and some process that will do quantum Fourier transform the way that really takes inputs to outputs in the right fashion.
Do we use angles? No. We use angles in Fourier. Okay, let me come back to that later. Let me come back. So probably Fourier should be scrapped at this point. It will come in back later. I forgot about the angles. I was just summing up everything I knew. But I think all the rest is okay. So complementary observer, GZ, CPM, POV1, Nijmerk, no cloning, no brokers. I think all the rest is okay. Quantum gate calculus, for those guys who get like GZ, C0, CZ, definability.
Do Fourier one qubit.
Yeah? And now I remember, we don't have, the only angles you've got here are pi over 2. The only angles you have here are pi over 2. And for Fourier you need?
Well, you need pi over
4.
to the n for n qubits.
Ah, yeah. Wait, pi over 2. Yeah, okay. Okay, one important remark, this category doesn't have byproducts. So it's an interesting example for that reason. We haven't seen a lot of categories which don't have byproducts and which do this stuff for you. So here there is no addition and thing going on. This should be studied in more detail, by the way. Now, big question, where do these classical structures actually come from? So I was working with this with Bill Edwards, who's a student in Oxford. So he was checking a lot of these things. And then we bounced onto the following very weird observation. You remember that I gave all these examples of where you find complementary observables. Well, this one was a lie. And everybody believed it. Yeah? Ah. Okay. Thank you for shutting up then. But you knew it. You already knew it.
You mean whether there are two bases?
Whether there are two complementary...
I didn't believe it either, and I also didn't believe it for I mean, I knew my properties, and doesn't have any lifetime right.
Okay, nobody reacted before. Anyway, here they are. Here they are. So, we don't have to go further than a 2-element set. We go to a 2-element set. Yeah? So this is the obvious copying relation you would expect. This is the obvious deleting operation, which you have canonically. This is the ones. Now look, then you've got this weird beast here. You send 0 to the entangled state 0011, you send 1 to the entangled state 0110, and you take this as a copying relation, and then you can actually check that this indeed gives you a classical structure, and you can check that these two together satisfy all these axioms of complementary observables. Very remarkable. I find this shocking because I was so sure that would only be that REL would be different from all these byproduct categories in the fact that they didn't have complementary observables. Now, let me give a concrete calculation which shows what is actually happening here. So in Hilbert spaces, we would have this. We would have this as a canonical copying relation, yeah? You copy the base plus minus instead of 0, 1. Now, if you fill in these values, then you get that plus is mapped to, in those ones, plus is mapped to 0, 0, plus 1, 0, plus 1, plus 0, 1, plus 1, 1, which is plus, plus. Now, minus is mapped to the same thing, but with a minus here and a minus there. Yeah? And which gives you minus, minus. So, basically what is happening here, in some sort of implicit way, this guy is sort of accommodating negatives within relations. It's a very funny implicit way. I can't say more about it, but it's just weird.
So I have a question.
Yeah?
Is it time for?
Yeah.
I mean, so you also asked whether we have complementary observables in cobordism, and so in a way we can have, the way I was viewing it yesterday, we can have complementary observables, or we can have just one base, and we can have a unitary of order 2.
Yeah.
Now, in the cases, as Samson is pointing out, a lot depends on whether you have enough points or not. In cobordism, you don't even have this one base. You don't have any observables.
So what do you mean by a lot depends on points?
Well, how many morphisms out of your tensor unit you have? Cobordism is a free category, so except common or unit, you don't have any other points.
That's not true. You go into, like one of these things, right?
That is the unit.
No, the unit goes into 1. So,
Okay.
you go from
So I think I'm continuing. Okay. This is becoming a debate. No. No, this is becoming a
Can I
debate.
finish? Just 2 more
Yeah,
seconds.
what can I finish? I don't see. I'm missing the point where you're going, but I'm just trying. So anyway.
I didn't get there yet. I didn't make it.
Well, yes, then it's a lot. So, just on the issue of points, what is missing here is exactly that there are no points. This point, minus, is not living in this category. But still, the copying operation and deleting operations are living there, as this classical structure. So, despite the fact that you don't have the points, you still have the ability to express quantum phenomena. And I'm just going to prove you one. I'm going to show that in category of REL with 2 bits, you can simulate quantum teleportation in a faithful way. With classical communication.
That is what I was going to ask. Can you not represent incompatible observables even if you don't have points? So in that sense, then
so complementary observables give teleportation. Now, so just to show this, the statement, you can prove the following: that the structural resource required for quantum teleportation, including classical data flow, is something which is called a Bell-based indexed over a classical structure. You can prove that if you got that, then you've got classical teleportation. And the other proposition you can prove is that given 2 complementary observables, like a scaled bialgebra, like Ross described this morning, induce such a Bell state indexed over classical structure, and this is this. So this is basically your index in classical structure. This is your first quantum system, this is your second quantum system. So I think I'm running out of time, so I'm just going to rush over this. So I just have to say what a measurement is quickly. A measurement is something which is a quantum system as input, quantum system as output, and produces some classical data. because the idea is to have classical data flow. Then you assume a bunch of axioms. Like, for example, this is von Neumann projection postulate, which is a reasonable axiom. And then you've got some other axioms. I've shown this before. And then basically you show that with these three axioms, if you apply them in Hilbert space quantum mechanics, you exactly, this is in the paper with Dushko, you exactly get that the Eilenberg, well, that the things which satisfy these three pictures are exactly quantum measurements. Like spectra of self-adjoint operators, spectra of projectiles. A more high-level categorical view is that they are actually the self-adjoint Eilenberg-Moore algebras induced by the classical structures. So that's a more abstract view. The concrete view is you satisfy three pictures, and then you exactly get quantum measurements. So these are these three pictures. And one example of a canonical quantum measurement is actually provided by a copying operation. So here you've got it. So these two actually together make this Eilenberg-Moore called Eilenberg-Moore conditions. So if I now plug in my copying operation, then I see that I exactly get back my classical object structure. Here is Frobenius, there is associativity, unit law. So we have a canonical one, which is the copying operation itself. Now, what is a bipartite quantum measurement? Here is a bipartite quantum measurement. This is a projector. We can analyze the projector as follows. So bipartite quantum measurement must look like this. Yeah? This is bipartite quantum measurement. This is like a projector, bipartite projector. So this is bipartite quantum measurement indexed over some classical structure, and then from the thing we had before, and then you can show that you've got a bunch of axioms to assure that this is a measurement, and then you can prove teleportation with classical information flow, very simple. Similarly, you can prove tank coding just from these axioms, and this guy basically gives such a basis in this way. So just having these two complementary observables is enough to simulate teleportation in the following, in the following way, and then you've got a proof for correctness, which is just something like this. So everything is satisfied if you just have these two complementary observables here, which are provided on the two elements set by it. So if you have if you axiomatize your classical structure in terms of biproducts, you cannot do this. I'm not saying that it's worse or better or something like that, but you got this magically thing happen when you work with classical objects, that you actually can do teleportation on two elements. So some other nice stuff, and this is now going back to the Fourier transform comment. So we have these two very simple models which I just gave. There is the Speckens model, and there is a much simpler one of these classical structures on two element set. Now, what is the interesting next step you can do, model-wise, is you just add new features, new elements. And for example, Prakash is now not looking, but worked on, for example, this state, which is the W state. So if you introduce, instead of pi over 2, also the angle pi over 3, you can basically simulate the W state. And so the idea is you're actually doing Lego theory. You're just adding little pieces to your theory.
Is that still a subcategory of Rho? Or is it just some freely generated algebraic?
This one, I don't know where you can get this. This is more axiomatically now.
The two things you had before were both subcategories.
Yeah. Yeah. Now this is something you would add to REL, I guess, as a new generator. It's closed because it's a division in 6.
So do you automatically get pi over 4 once you have 3 combinary terms?
You get pi over 2, that's the best you get. In Speckens model it's only pi over 2. That's why you don't have W state there. You don't have W state in Speckens model. Yeah. This is all. This is all very. This is just a bunch of a lot of recent stuff. So I think. I guess I've spoken for an hour or something. So I should stop. There's like loads more. Yeah. So I just want to make one comment for Key. And that's. So years ago, when Key and I, we loved each other, and we spent a lot of time together.
Don't say that on
So we took something of this shape, so simplex, and we ordered it. And basically these are classical probabilistic states, this thing. Yeah? These classical probabilistic states. And we put a partial order on it, which we call the Bayesian order. And then we wanted to have partial order on quantum states, so what we did is in some way we glued a lot of these guys together. Yeah? Now, in this little model which we just had before, basically it's built on these two glued pyramids together. Yeah, that's what it is. This is the Speck-and-Stoy model. You've got these 6 mutually orthogonal states. And so you can actually embed them in this simplex. And if you want to look at mixed states, you just convexly close them. So you get a partial order on quantum states within the simplex, which is different. That's it. Okay. Yeah, hey. So these were a lot of loose ideas, but okay. Yeah?
So, in RHEL, you got the two example base and complementary buffer structures for two on the set, right?
Yeah.
So Hilbert spaces always construct these by dimension. You don't see them, right?
In Hilbert space you can always? No, we know nothing more about that too. So basically we had a bunch of stuff. We had some stuff in 4, which was the Speckles model. And so in a way, this one is a projection of Speckles model on 2 dimensions. It turns out you can factor them. You can factor this definition which I gave of this copying operation in 2 parts which both look like this. That's how we got to this one, actually. Yeah, Samson?
Yes, well, it's not really a question. I mean, my sense is there must be some kind of general construction.
Definitely. The interest of this is just like some wild ideas, but this is...
I mean, but maybe, sort of, it could be something like, something can iterate, so you get discrete models that are finer approximations.
Yeah.
So at some kind of inverse limit, maybe you get, more or less.
This is very much unfinished stuff, but I think it's surprising insights that you can actually get these incomparable things in RHEL. So there's a lot of things to be checked, and at the moment it's like dirt to check in.
If you're using equal lengths, like picking your 2 favorite agreeable groups and getting more than actual can be a model.
Yeah.
I have a question, or actually I have 2 questions, but sorry, did I? You were continuing to discuss the first issue. So one had to do with, so at various times, Rob has interpreted these subsets as equal probability of the ontic states, and then there are larger subsets that don't have exactly. So let's see, do all of his epistemic states have exact information, ignorance balance? You can have
But it
mixed
depends.
states where you know less, right?
Yeah, yes. You get that's
sort
one
of-
of the comments which I made. If you apply Selinger's construction to this category, you obtain his mixed states.
You obtain whose mixed states?
Packets, Rob's mixed state. So he introduces the concept of like not maximal information. That here they arise from general categorical construction, the same ones.
This is what you call the CPM construction.
CPM
But
construction.
but you don't get all probabilities.
What do you mean all values?
Like 1 over 2 to the n or something. So
No.
you get all probabilities.
Yes.
Okay.
Well, the thing is, there are not that many numbers here, so it's a relational model. You could artificially introduce them. Take a category where you have these things, but
So in sometimes we
here,
talk,
0, 1.
sorry, what? Sometimes we talk about the convexification of Rob's model.
So yes, this would be a construction. But in a way, you can do convexification without numbers. What?
That's what this must be saying.
Yes.
What Selinger must be saying, or applying Selinger's
No,
model.
I mean, well, the fact that all this is happening while you still don't have a lot of scalars around.
Yeah.
So I guess I was wondering if you think convexity is related to having a bipolar structure or not. Does Selinger's construction
No,
thing
it's
then on that one?
purely multiplicative. It doesn't rely on any additive structure. And And like the argument which Samson give this morning, you have a feel, people always started this as it's something to do with linearity. Like copying, and there it's purely topological, so you don't have additive structure. But multilinear structure, but still that's a different thing.
So can I try to ask a question?
Yes, now you can.
I mean,
But it was a comment you were giving, not a question.
it is a question. I mean, I wouldn't be going on with it. I mean, if you have a classical object, if the tensor unit generates, then you can express it as a base by extracting these elements which are copyable in the little. If it doesn't have, if the object doesn't generate, you can still do your thing. So, for instance, then in cobordism, although Rick said it's not true, if you fix a type, you only have one cobordism from tensor unit going there. So so it's never going to generate. Could you do, instead of having your incompatible observables as morphisms out of the unit, would you represent them as endomorphisms on your type, or unitaries on your type?
That's not clear.
So, do you
in the way I produced, I did it in a little bit, because I generated this from these underlying permutations on the forum and said that, so that's in a way doing that. But the thing is, these permutations don't become permutations on the higher level. They are permutation on the ontic level, they become genuine non-classical unitaries on the epistemic level. So that's part of the trick.
Because, I mean, it's kind of important to me. That would be the categorical way to do it. And on the other hand, it seems to me that at least in quantum papers that I read, that no one is doing it like that. That people are really doing it with the actual observables.
Yeah. So I don't know. I think there's a lot of things to be done here. We didn't have a lot of models, and I think now there are a couple of interesting models to stare at, which are very different from those we have been considering so far.
A general question: to which degree do you sense that it is important for you that you have the actual vectors, that you've got enough stuff coming out of tensor unit to really move around the elements?
I don't think it's very important. Like in Ross, this might be confusing in the talk which Ross gave, but Ross gave the points in order to prove bi-algebra law from copying law. But in general, you don't need points. You can assume structures which don't have points, and I just gave an example. He used this to prove the bi-algebra law from the copying law.
For the record, there are infinitely many points from tensor unit to one circle that are two-dimensional cobordisms, because the space of scalars is huge, right? Every closed manifold is a scalar.
So do they generate?
I don't know what that is.
I have a question.
Yep.
So, it's not going to be a very precise question. It's, so it seems that you're converging on a nice quantum framework, which is not Hilbert spaces, but it's something more abstract. And you've got many different examples. And what can we expect in terms of transferring what we get in one of those little models into the actual, into another one, and in particular into the one people are used to? Can you go from one to the other? Can we conclude? Can we refute something by going into a finite model?
Are you taking model checking or something like that?
Yeah, for instance,
Well,
can you
maybe to sharpen that, and sort of add something that I'd also occurred to me. I mean, are they going to be, what are the factors going to be between these models and other models in a particular open space? I think they have to embed this in a natural way in open space.
Yeah. Do we have a category of such dagger categories with classical objects?
Yeah, no problem giving a definition, but the actual
Can we go through? What would be a very simple example of I want to solve a problem, an easy one, one that I already know how to solve, let's say, and I go into one of those funny little time models, And here it's really trivial, and then up I transfer.
Ah, okay.
Yeah, that would be, I mean, actually, one thing we considered at an early stage was Hilbert spaces as a realm, but it would actually be much more interesting to look at possibly retractions, where you can embed this back in lots of interesting ways.
So one of the things which we got one thing out of this so far, and this was like we were looking at GHZ states and W state like with a limited set of structural resources, and we, for example, found very easily, which I don't think you would have easily found otherwise, that there is actually more than one W state with completely different behavioral properties. So they live in the same slot class, but they let you do different protocols. And this you very easily saw from these pictures, because there's like you can generate the W class, and W class means all the angles are up to pi. And then you can play with it. But there is another part of W class which is 2 angles minus the third angle are up to pi. And they have completely different behavioral properties, not completely different, but they are.
What does it look like when you lift it back to grid space?
It's just ugly. You don't really see it. It's been with playing with this thing that we actually came
You
upon.
do leader election with it and things like that?
Yeah, well, yeah. There's enough structure and to derive.
No, I mean,
For
other
example,
one.
you're proving implicity results in the precisely in this respect. So maybe can we obtain a shorter argument if we go into finite model?
No, it'd be interesting.
Yeah, so a lot of this thing is just in progress now. It's just a bunch of time.
So I was interested in this W state thing.
Yeah.
Though you thought I wasn't looking, I was. I was actually looking at your webpage.
Ah.
What do you think of the photograph?
The photo, I didn't look at the photograph.
Well, that's good, it's a blank.
So there was this LU-LC conjecture, for instance.
Yes, yeah, which is fun. Yeah, yeah.
Which is
So one of the things we should definitely go into that is like graph states and more general stuff, because graph states are a subclass of this. Obviously, they're quite trivial. They're just like a green alternating with the age and the stuff. So then there is, I don't know, maybe Ross has been looking a little bit at that. I'm not sure. Maybe.
The graph state is locally equivalent to just two-color graphs. Where every vertex is a key.
Sorry?
Where every vertex has an open edge. But that's, once you got this, the syntax polygons, that's what it is.
I'm already packed.
I think something like the LU-LC conjecture would be a good. It's the kind of because you would expect to refute things in a finite model.
Yes.
Rather
Yeah.
to establish things. I'm not saying that particular statement, but something like this, which is difficult but gets simpler
I see.
in a finite model, and then you've got your.
Yes. No, I would imagine that should be possible. So, like Ross is building a tool for this sort of stuff, and then just feed stuff in it. I guess I don't know what the specification is of that tool, but it's a tool.
It's totally replaced the whiteboard. It's
Yeah.
built up very quickly.
I'm just wondering about the possibility without the mark that you made. So supposing you go to a toy model and show that something is impossible. It's not obvious to me how that lifts back to the
Yeah,
That's
there
why
was-
it would be interesting to see factorial connections.
Yeah, no, so I'm not saying it's clear to me, but I'm saying this, like, my gut feeling would be that I could use this kind of thing for refuting statements like the LUS conjecture that something, if it's default equivalent, if it's locally unitary equivalent LU, then it's locally default equivalent, and it's not true, and it's a little rough on the edge. The proof, the counterexample, which is not very easy to understand, but maybe design a machine like this, you get a rational reconstruction of the counterexample.
Start to dream, you might think that for every particular size of finite dimensional system with a finite number of sort of angles and so on, there'd be some size of finite model that was faithful.
People are doing this kind of thing. People are using finite fields to do.
Yeah, yes, yeah. So that's something like Bill is looking at now. Like how different is using a finite field and then a calculus over that, like a two-element field. It's like a simple example. What is different from like this two-element model? So there must be some difference if you start with finite field versus the Boolean summoning. Both have now incompatible observables. So these are like interesting little questions about.
So you're also putting information into the subcategory.
Why do you see there are little questions?
Huh?
Why do you see there are little? I would say the major. No? Is there anything else you have in mind?
No. Little, I don't mean pejorative.
little
I mean,
in the
it's like
sense
not
of
fancy, not
yeah.
like, hey, I've got a fountain and I've got a seven category, you know.
So,
No, I agree with you. These are the important questions.
So your 50-minute talk is
Models,
still over,
models.
and I think we need to take a break. So we'll do that now. But let's thank all of you.
Oh.
So we're going to reconvene